Right, so in this video I'm going to be explaining another important paper with the title graph2vec, Learning Distributed Representations of Graphs. This paper in 2017. Recent works on representation learning for graph structured data predominantly focus on learning distributed representations of graph substructures such as node and subgraphs. However, many graph analytics tasks such as graph classification and clustering require representing entire graphs as fixed length feature vectors. While aforementioned approaches are naturally equipped to learn such representations, graph kernels remains as the most effective way of obtaining them. However, these graph kernels use handcrafted features like shortest path, graphlets, and etc., and hence are hampered by problems such as poor generalization because it's a handcrafted feature. So we propose a neural embedding framework. We call it graph2vec to learn data-driven distributed representations of arbitrary sized graphs. Graph2vec's embedding are learned in an unsupervised manner and are task agnostic. Hence, they could be used for any downstream tasks such as graph classification, clustering, and even seeding supervised representation learning approaches. Modern neural embedding methods such as Word2vec use a simple and efficient feed-forward neural network called skipgram to learn distributed representations of words. So, given a sequence of words like W and W1 to WT, the target word whose representation has to be learned, and the length of context word, the objective of skipgram, skipgram, if you should maximize this. So these are the contexts of the target word WT. And the context word and target words are assumed to be independent. So this is one background you need to know. Another background is, look at this one. The posterior could be learned in several ways. For instance, a naive approach could be using a classifier like logistic regression. However, this is prohibitively expensive if the vocabulary is very large. So, negative sampling is a simple yet efficient algorithm that helps to alleviate this problem and train the skipgram model. Negative sampling selects a small subset of words at random that are not in the target word's context and updates their embeddings in every iteration instead of considering all words in the vocabulary. So if a word W appears in the context of another word, then the vector embedding of W is closer to that of W prime compared to any other randomly chosen word from the vocabulary. Also recently there is another paper, Document2vec, which is a straightforward extension to Word2vec. So the model works by considering a word WJ to be occurring in the context of a document D sub I. So we want to maximize this, maximizing this probability. Now, what is the method of this paper? We extend in graph2vec is to view an entire graph as a document and the rooted subgraphs around every node in the graph as words that compose the document. So there are two reasons that make rooted subgraphs more amenable for learning graph. First, high order substructures, and the other one is nonlinear substructures. Compared to linear substructures such as walks and paths, rooted subgraphs capture inherent nonlinearity in the graphs better. This fact is evident while considering graph kernels. For instance, WL kernel, which are based on nonlinear substructures, offer significantly better performance. So this graph2vec has two main components. First, a procedure to generate rooted subgraphs around every node, and the second, the procedure to learn embedding of given graphs. So once we have a graph G, the output is matrix of vector representations of graphs. Here we are getting the WL subgraph. And in this algorithm, the output is the rooted subgraph of degree D around node N. So once we have these rooted subgraphs, we can do skipgram with negative sampling. So their data sets are very popular mutog proteins, these benchmarks that we use for graph classification. And they compare it, for example, to Node2vec, which is a very old model.